Assalamualaikum and good day everyone. So today I'm going to describe on how to answer question 3 and question 7 of computer-based tests using Excel. So let's start with question 3, which focuses on delta gamma H of Barry's position, where we can describe it in form of V is equals to put plus N1 call plus N1 stop. So in this case, we can see it's positive put because Barry purchased the put option. So it's a long position, and the N1 and N2 we should find, and the call is the call price, the at the money European call option with 60-day maturity, and the stock is the stock price given for 27 days. So Barry wants to rehedge his position daily. So daily means our T minus T initially is 60 over 365 because it must be in form of years. So if daily means later we have to keep doing it for 60 over 365 minus 1 over 365 until 27 over 365 because we have 27 days and we want to observe the profit or loss for each day over the 27-day period. So when we focus on this equation, V is equals to P plus N1C plus N2S. Sorry, this should be N2 here. So we can come up with a detailed profit or loss, where when we want to understand the profit or loss has three different components. Number one is the derivative component. So in this case, our derivative, we have two. The first one is put and the second one is call. So in order to find the derivative, the formula is, so for put, we only have one put mentioned, which is Barry bought only one put. So 1 times with put at day T minus with the previous day price of put. Same goes for call, but call, we have the N1 value here. So the N1 is equals to call T minus with the call price of the previous day. So when we do the T minus T for each day, so we can eventually find the put price and call price for each day. Then number two, we can focus on the, the first is the derivative part. Number two, we can focus on the stock component. So the stock component, we will use our N2. So N2 of the previous, which is at start, of course, the time equals to 0, the day 0, 1. So N2 times with ST, which is the price at day 1, the price at day T, exponent delta power H minus with S T minus 1, which is the previous. So this is the previous. So when we start with day 0, when we start with day 1 here, so this become S1, this will become S0. S0 is given in our question as 35. So that's the stock component. And then the final one, the third one is the money component, where money component formula is equals to negative V e power of RH minus 1. So again, when we write our V, right, is equals to put plus N1 call plus N2 plus N2 stock. So when we find the put price, the N1, the call, the N2, and also the stock price, so when we find the value of V, if we get the positive value, it means that we are borrowing. Because in this case, our put is a long, Long means our money going up. So when our money is going and then the N1, after we find the N1 and N2, we have to check what position is it, long or short. Is it long or short? So once we get the clarity on whether it's long or short, and we get the answer in a positive value, which means that the money out is more than the money in. So we do the borrowing. So once we have the borrowing, we just take the V value, we just substitute in this formula, and we can get the answer for the money component. So all these three component is findable if we are able to get the P value, N1 value, C value, N2 value, and S value for each day. So of course, in order to find the N1 and N2, in order to find N1 and N2, we have to use we have to do the delta V over delta S, which is equals to delta put plus N1 delta call plus N2 equals to 0. And then delta square V over delta S square is equals to gamma put plus N1 gamma call is equals to 0. So from this, right, we can eventually write our N1 is equals to negative gamma put over gamma call, and our N2 is equals to negative delta P minus negative delta P minus N1 delta call. So we can use this in order to find the answer for N1 and N2. But for that, of course, you also need to know the formula of delta put, delta call, and also the formula of gamma put and gamma call. So gamma put and gamma call is basically having the same formula, but in our question, both of them are having a different K, so the value of D1 will be very different. So negative R T minus T S T sigma T minus T, and then times with 1 over 2 pi square root exponential negative 1 over 2 times D1 squared. So for both gamma and put, you have to do it separately, although in definition they are the same, but you have to do the calculation separately because the D1 value will be different due to the difference in value of K. For call, we can see the value of K is 35 at the money. For put, the value of K is 36.5. And also the delta put is negative exponent negative RT minus T and negative D1. And also for delta call E negative RT minus T and D1. So we just substitute all these formulas in Excel for day 1, then we can drag it until day 27. So as I have done here, for T minus T, at first is 60 over 365, and then followed by day 1 until day 27. And then the ST is just taken directly from the question given. And these are the infos for European put and also the European call that is mentioned. This is the derivative part. And then for long position put, of course, we find the D1. So D1 is long, only focusing on the put here. So we only use the data from the put. So we do the S naught over K plus R minus delta plus 0.5 sigma squared times with the T. So in this case, we must take the T. The T values will always change because the price changes by day. So your D1 value, your D2 value, and your N negative D1, you use the norms this function. Same goes for N negative D2, and we will get the put price. Once we get the put price, of course, we can find the delta put by using this formula here that I write down. So we can find the delta put and also the gamma put. So once we do for one particular row, so we can drag for all the 27 rows for the 27 day. So the change in put price, why do I do the change in put price? Because in component one, we need the change in put price, which is the PT minus 1, which is the price of this day minus the previous day price. So of course for day 0 is nothing, and then from day 1 onwards you just drag the put price from day 1 minus day 0 until day 27 minus day 26. It's done for put component. Now for call component, of course we have our D1 and D2, the same stuff, but using a different value of K. So using the European call basis here, where the K is equals to S0, since it's at the money. So the same step do for the D2, which is D1 minus sigma square root of time, and then ND1 and ND2, and then we find the call price. So the call price and put price, maybe I can also write the formula here. So for put price just now, P is equals to KE negative RT minus T and negative T1 minus with S E negative R T minus T and negative T2. So the S value, it changes every day, but the K value keep the same. For the call, SE, this is delta, sorry, negative delta T minus T and D1 minus KE negative R T minus T and D2. This is D2, this is D1, sorry. So for put, this is the formula. The K remains the same. S will change every day. For call also, S will change every day, but the K remain the same, which is the add the money, which is the 35. So we can get the call price. Of course, we can use the formula back again to find the delta call and also the gamma call. Delta call and gamma call. And we drag for all the 27 days. And now to find we can find the call, the derivative component for call by finding the change in call, which we need the N1. N1 formula I have mentioned is the negative gamma call, sorry, negative gamma put over gamma call. Drag for every day. Then you can find the change in call by using the N1 values. Take the first day price divided by the previous day, and then the next day price divided by the previous day. And then moving on to the stock, of course, we find the value of L2. Once we get the value of N1 and the delta call and delta put, we can find the value of N2 in this case. So this is our N1 and N2 formulas, and we just apply it in the Excel. We drag, and for the stock component, these are our values for the stock component. We can refer to number 2 here. So just apply that. We take the previous N2 times with the current price of the day with the exponent delta H. H is 1 over 365 in this case. And again, once we have all the values, we can find the value of V. So in this case, our V's are all positive for all 27 days, which means that we are borrowing. So when you have a long position of put, short position of call, and long position of stock, so your money out is higher than the money in. So this is your short position of money, which is the borrowing. So when you do the borrowing, you can find the money component values, which is negative V times with the, we have the formula at number 3 here, negative V times with E power RH minus 1. Finally, to find, so of course, when you do for day 1, you can eventually run for all the day 27. And then for daily profit or losses, we just add the final answer for change in put price, and then the change in call price, the stock, and finally the money component. Then when we drag them down, we already have the profit or loss for all the 27 days. Then we use the sum function for all the profit or loss to get the total accumulated profit for 27 days. So that's all the explanation for question 3. Now let's move to question 7. So the question 7 mentioned here about the currency. So a London fashion designer is expecting to receive 100 million yen from a Japanese company in 1 year. So company decide to hedge risk by purchasing an option that grants the right to exchange yen for pounds. So they are given the spot exchange rate, the volatility, again the risk-free rate for yen and also the pound. So the first question is to calculate the cost of hedging using a 12-period binomial tree, using 2 approaches, which is pound and also the yen denominated. So first of all, we must understand the pound and yen denominated. So pound denominated means the domestic is always the pound and the foreign is yen. And I must assume myself as British, where I have 100 million after 1 year. Since the domestic is the pound, so I must sell the yen in order to exchange for the pound. So this selling activity is of course the right to sell. So we use the put option to find the pound denominated. So in order to do the yen denominated, is I must assume myself as Japanese, where the domestic is yen and also the foreign currency is the pound. So I get 100 million yen after 1 year. Since I'm getting my domestic currency, so I can use the 100 million to buy and exchange it for pounds. So when this buying activity, the right to buy, so we use call. So for yen denominated here, we use the call method, and for the pound denominated, we use the put method to find the cost of hedging. So how we do it in the binomial tree? Of course, in binomial tree, we first need to find the value of u and also d. So these are the formulas for u, exponent r minus rf, h plus sigma h, and the d, exponent r minus rf, h minus sigma h, and the p star is equals to exponent r minus rf h minus d over u minus d. So this is a 12-period binomial tree, so our h is equals to 1 over 12. And of course, our r and rf will change based on is it pound denominated or yen denominated. If it's pound denominated, this is pound and the foreign is yen. If it's vice versa, it's yen and pound. So for pound for the exchange, we first use our exchange rate. So we have 0.005. So for pound denominated, we just use the original given in the question. Also for the K, we use the original. The domestic is the pound and also the foreign is the yen. Then for the exchange rate for time 0, so we have the binomial tree here. This is step 0 means time 0. Then for time 1, we use the if function, where it clearly explains that if the function is blank, then we use another if function inside. So if the function is blank, then the answer is blank. But if it's not blank, then it's f2 times with c9. So c9 in this case is your d. So we're using, so binomial tree basically when we draw it, it's basically the s, and it become su, sd, become suu, sud, and also SDD. So we are just trying to denote that if there's no value here, so going down is no value. But if there is a value here, going down is times with the value of D. D is going down. So we just keep doing the same if formula. We keep doing the same if formula for all the functions from time 0. So if you want to see it clearly, from time 0 to time 12, we use the same, from time 1 to time 12, we use the same if function. So we can eventually drag them to get the binomial tree. So this is how the binomial tree looks like for the exchange rate. And now, since we're going to use the put, so we have to do it backwards from period 12. So for put, the maximum is the K minus with the stock price at time 12. So either the maximum of them or 0. So if you are getting negative values, your answer will automatically become 0 when you use the maximum function. So this is only for the period 12. But from period 11 onwards, we must use the formula of, we must use this formula. So again, we are using the if function just to eliminate the blank functions so that it doesn't disturb our equation. So the if function, again, we use it, but now we use the P star times with the, so as we can see in this question, so they use the P star times with the right cell plus with the Q star times with the right below cell. So when we do that, we are denoting the probabilities for each of the payoff. So the whole thing, when we times with e power of negative RH, so we will get the price. So we are using the probability times with the payoffs plus the down probability times with the payoff for each cell. Then we can times each of them with the discount factor e power of negative RH. Then we can get the price at each period. So this particular step only applicable from period 11 until period 0. So you can, at the end, you can find the price of put at time 0. So the cost of hedging is, of course, we have the 100 million yen, right? So 100 million yen times with the put price here. So we get the final answer. So the same step is for the exchange rate for the call. But in this case, for call, for yen denominated, of course, we must change the x naught, which is 1 over the original x naught given in the question. And the k also will change to 1 over the original k given in the question. Because when we look back at the question, they mentioned that it's 0.0055 euro for 1 yen. So when using yen denominated, we have to do 1 over 0.0055 for the K. Same applicable for the X naught. But the R domestic and R foreign also will change because now your domestic is your Japan and your foreign is your British. So when you change all these values, of course, your U, D, P, and Q values will also change. But your H remain the same, is 1 over 12. You apply the same step for the exchange rate, but using the new X naught values, like we did for the previous exchange rate binomial tree. But now, since we are using call for yen denominated, so of course, the last cell, the period number 12 cell will change to maximum of ST minus K or 0. So if you're getting any negative values, the answer will be 0. So once we only change that cell, the other cells remain the same from whatever we did for the put above. So your final answer for the call price is 21.5331974. But for the cost of hedging, we have to take the 100 million divided by the value of K. We need to do that because of the concept. We have to do that because of the concept. Because of the concept where it's given yen, we have the K value, the yen K, which is 181.82 is equals to 1 euro. So now our yen that we have is 100 million. So in order to get the price in form of euro, the cost of hedging in form of euro, so you have to divide the 100 million yen, divide with the value of K, then only you times with the price of call at time 0. So you will get this cost of hedging for yen denominated. If you want to check your final answer whether it's correct or not, so you can take back your yen denominated times with the original, which is this X naught. So when you do that, eventually you will get your pound denominated cost of hedging. Or if you do vice versa, you take the pound denominated, times with the X naught of yen denominated. So you will get your yen denominated cost of hedging. So this is how you check your answer whether it's correct or wrong lah. And that's done for yen denominated call option and pound denominated put option cost of hedging. And then in question B, so if you look at question B, it wants us to calculate the price of option by conducting a simulation of 1,000 iterations. So in this case, for 1,000 iterations, we have to create the sequence for 100,000. Sorry, the question was 100,000. And then for the value of U, we just use RAN and then the bracket. So once we do that, we can run the RAN values for 100,000. So if we control shift down, we can see there's 100,000 values here. Okay, then for the Z score, we use the norms because this is a standard normal. We're going to find the standard normal inverse. So we use the norm as inverse of the U so that we get the Z score. And for the exchange rate, so this is 1 year, right? So your exchange rate, it works same like the Black-Scholes framework. So your x1 is equals to x0 e power of r minus rf minus 0.5 sigma squared 1 plus sigma 1 and then the Z score that you find earlier. So you can use the Z score that you find earlier to find the exchange rate for all the 1,000, for all the 100,000 data, random numbers. So then you can also find your payoff. So in this case, your payoff, you can choose either put or call based on whether you want to use your pound denominated or your yen denominated. So in this case, I use the pound denominated. So that is why all my data here, the X naught, the K, the R domestic, and also the R foreign follows the pound denominated. So if I want to use the pound denominated, of course, my payoff is must be the put option, which is maximum of K minus the exchange rate. So for put is maximum of K minus exchange rate 0. So I use that formula to find the payoff. And once we get the payoff, in order to find the price, we need expected payoff times with the, so price is equals to the average of payoffs, and then we times with the e power of, we times with the discount factor, which is t, sorry, e power of negative RT, and then times with the 100 million. So I find my expected payoff above. So expected payoff is just the average of all the payoff from 400,000 data here. And we get the price of put option, which is the expected payoff times with the discount factor. In our case, it's 1 year, so we use T1, and also we take the R value of pound because we are focusing on the pound, and times with 100 million. So that's our final answer for the price of put option. So that's all from me explaining question 3 and question 7. Thank you so much.